All right, this video is on 2-8. So we're specifically focused on segment proofs. Previously, we worked on algebraic proofs, so solving equations and then identifying properties that we use to solve an equation or multiple equations. Now, because this is geometry, right, this is all leading to geometric proofs. We're going to get to segment proofs today and then angle proofs the next day. Now, within addition to the notes that you have, you're going to use a couple of pages, I think potentially 2 to 3 pages here, and then the assignment. You should also have a half sheet. This half sheet will be a part of one section of our notes, so just make sure you have that. Okay, so before we get started, or before we get to proofs, let's get started here on segment proofs. So these we're just dealing with properties, and as you can see for segment proofs, we have properties that help us with equality, properties for congruence, and right, you can continue on from there. Right, we have definitions, and then we also have postulates. Okay, right, and this is something that we're familiar with. Segment addition postulate, that was actually our first section of notes. But let's go ahead and get to here. Some words we see that are familiar, right? Reflexive, symmetry, symmetric, and transitive. But how does that relate in a context or a geometric context? And so it says the properties above may only be used with equal signs, with equal signs. The properties of congruence below can be applied using the congruent symbol. So, right, equal sign, we have this. Congruent symbol, we'll have this. Right, just remember the equal to part means same size, the squiggle part means same shape. So congruence means same shape and size. But getting to reflexive property here, for any segment AB, we can say that line segment AB is congruent to itself, line segment AB. Now, whenever we have that line segment above, right, that tells us we're dealing with the shape, so we can only use congruent symbols for shapes. We do not use equal signs, right? We'll talk about that later. All right, symmetric property of congruence. If line segment AB is congruent to line segment CD, then, right, symmetric deals with reflecting, kind of a mirror image. You can say the converse of that is true. CD, line segment CD, is congruent to line segment AB. And then finally, the transitive property of congruence. We have still dealing with these line segments here. If we're saying line segment AB is congruent to line segment CD, and we're saying line segment CD is congruent to something else, let's say EF, then we can say line segment AB, the first thing, is congruent to line segment EF. All right. And then now let's get to definition of congruence. So we're going to be going back and forth between focusing on the shape of an object, between focusing on the measure of an object. So it says segments are congruent if and only if they have the same measure. So if, I know we're writing A's and B's a lot right now, but we'll just continue. If line segment AB is congruent to line segment CD, then we can say the measure of AB, which is just AB without anything else, without the line, is equal to CD. Okay, so when we talk about measure, we just use equal signs, and we do not have the line there. And vice versa, in an if and only if, a biconditional statement, we can say, because the definition of congruence, we can also say the opposite. AB is congruent to CD, is equal to CD, then the line segment AB is congruent to the line segment CD. All right, just setting it up for now. And then, right, another definition of a midpoint. Right, so we talked about this, how to calculate this in Unit 1. If M is the midpoint of AB, then AM, right, this part of the line segment here, or this is its own line segment, is equal to MB, right? That is this part right over here. This equal to this, and sometimes we'll see it annotated on. We'll put a tick mark to represent that those are congruent. And then finally, the last property that we're going to deal with, segment addition postulate for line segments. If A, B, and C are collinear, as they are here on the straight line, and B is between AC, it doesn't have to be on the midpoint, just somewhere on it, we can say the AB plus BC, right? So this line segment plus this line segment is equal to the entire thing, AC. Okay, so we're not talking about the shape itself, we're talking about the size, and these would have measures in place of it. Okay, now what I'd like for you to do at this point is on the next page, go and identify which properties are involved, whether that be addition, subtraction, multiplication, division, even, right, any one of these properties as well. I'd like for you to pause the video at this point, and then when you're ready, hopefully you spent like 3, 4, maybe 5 minutes to identify what these things are. Then move on to the next page so you can just check your understanding, right? Do you understand the various properties of equality, congruence, definitions, and postulates? Okay, I'm going to move on to the next page though, so you can at least see it. But at this point, pause it. I'm going to wait. And we're going to go to the next page. But again, try it first before you look at the next page. All right, here we go. Okay, so as you can see, from numbers 1 is a 14. We have a reason bank here, so you can identify which one maybe belongs with which. But the first one is definition of congruence, right? If we don't have the line segment, just dealing with the measure, right? Even though it's equal to itself, this is talking about congruence here. It's not reflexive. 2, right? If K is between JL, right? This is segment addition postulate. I just put POST for postulate there. We have the reflexive property dealing with these line segments. EF, line segment EF is congruent to line segment EF. And you can go on from there. So in order it goes addition property of equality, symmetric property, definition of a midpoint. I just abbreviate midpoint in an unusual way, MID, and then PT. Transitive property, subtraction property. Number 9 is substitution property. Then we have definition of a midpoint, definition of congruence, subtraction property again, division property, and transitive property. So it's going to be hopefully, right, our understanding that we now know how to apply these properties, or understand these properties. Now we're going to apply them. Okay. All right, we're going to look at this next one. So this is the half sheet that you should have. We'll be referring to this, and ignore this. It's just supposed to be one side. So just looking right over here. So as we go through these various problems, we're not going to do all of these, but like an example for, let's say we were working on number 4, just giving you a hint, right? Number 4 is going to have these reasons throughout that proof. Maybe, I'm not sure if it's going to be in that order. I don't think it'll be in that order, but yeah, so just refer to these when we get to the next page. Okay, so right here, as you see, we do have assigned number 1. So you want to look at number 1 and which properties are we going to be applying as we come up with an argument here. Okay, and just realize here, right, if you look at number 1, there are some numbers, but almost no numbers here. Right, really, this is assessing our level of problem solving. Are we able to come up with an argument to support any claim that we're trying to make? And here, what we have for number 1 is EF is the midpoint of line segment DF. We can see that here, but it's not enough to just say, yeah, it's in the middle. Okay, how can we prove it without using a compass, protractor, straight edge, without measuring, just by making these various claims and warrants, or statements and reasons? Okay, so what we want to come up with at the very end is that 2D, or 2 times D, is equal to DF. So if I have this, 2 of these, if I put those side by side, is equal to the entire thing. And that would prove, right, well, we're going to use this midpoint here in order to prove that 2 of these is equal to this entire thing. Okay. So for number 1, it says E is the midpoint of DF. Just like how algebraic proofs, we do have some given statements. So let's go and put given. But there, where we have to use other things that we know to be true. So if E is the midpoint, we know that whoops, I thought I had my highlight. DE is equal to EF. So this is equal to this. I'll annotate it here. What tells us that those two things are equal? if you look on the previous page properties, this is the definition of a midpoint. The definition of a midpoint states, right, that we have two congruent line segments. All right, and then another argument that is made here is, well, if D is equal to F, right, we can come up with this: DE plus DE is equal to DE plus EF. What we did from this line to this line is we had the addition property of equality. I just added an extra DE to both sides here. So addition property, right? And we have to get comfortable in that there are going to be instances where we're not always going to know the argument. It's a very open-ended type of problem. The reason that we add, so the question is, why did we add DE to both sides? Or why do we add DE in the first place? As you can see here, I'm trying to prove this. I know I need two DEs here. And from here, line 3 to line 4, we have DE plus DE. You're going to notice that equals 2DE. I didn't simplify the right side. So this is 2DE. That's part of what I want. And that was from simplifying, combining like terms. All right, well, if we look right here, right, what else is coming up here? So we have DE plus EF is equal to DF. That is this plus this is equal to the entire thing. What tells us that? That is the segment addition postulate, right? One segment plus another segment is equal to that entire segment. So segment addition postulate. Okay. And as it's at this point here, oops, we're going to use these two arguments here on 4 and 5, right? If I take DE and EF, and notice how this is exactly the same thing, we can use the transitive property of equality and substitute. I can plug in now D or DF in for what's in blue there. So that is the transitive property. And that tells us, right, we have now then proven, you could say therefore, right, this statement is correct. 2DE is equal to DF, right? Two of these is equal to the entire line segment. Okay. All right, but this is just kind of our first example into trying to come up with an argument. Now this, all the statements were given to us, so this is definitely something tough for us to prove. But just being mindful of what am I trying to get at, going from point A to point B and working our way down from there, right, using these various arguments. We're going to skip number 2. We're going to go to number 3. Okay, so for number 3, you want to look at, right here, what are some properties that you're going to be using? So have that off to the side, right? So as we go through this, right, in which order are we going to be using these? I see, right, we have multiple different things. We have 2 substitution parts. We have definition of congruence twice. We have given. All right, here we go. So let's try to make sense of this because we have a lot of letters here. So we have that PQ is line segment PQ is congruent to line segment TQ. So PQ is right here. TQ is right here. And UQ, I'll put this as a double line segment, is equal to QS right there. What we're trying to find is, right, PS is congruent to TU, line segment TU, sorry. So how can we prove that? Or how do I know that they look, obviously they look the same shape and size, right? But how do we go about proving it definitively that it's true rather than just, it looks true, okay? So that's when we start with these arguments. So first of all, we're gonna start with given. We're saying, let me get rid of these highlighted parts. Right, let's just be mindful of what are we saying that are congruent for now. So we know that this is congruent with this. We know that this is congruent with this. Okay. Now, the next part here, it's exactly the same argument, right? Instead of line segments, instead of congruence, we have just the measure, and we have equal to. This is the definition of congruence. I'll put CONG. Okay. Now we know something else as well. This is saying PQ, which is this part in blue, plus QS, which is this part in red, is equal to that entire thing PS. Okay, right here. Yeah? And we have TQ, this part, plus QU, this part, is equal to the entire line segment right here. Right? That's just segment addition postulate. It's segment addition postulate twice, but we're just going to write, I'll put SEGM addition postulate, or add POST. Okay, we know that to be true. We know that if we take that blue and that red is equal to the entire line segment. Okay, but what other arguments can we make from there? We have TQ right here plus QS right here is equal to this entire thing. So this plus this is equal to this entire thing. The reason is because we just said that this blue thing is equal to this blue thing. So what tells us that? Right, this is the substitution property. And specifically, what am I substituting? If I look right what's above it, this is PQ is equal to TQ. Right, PQ right here is equal to TQ. So this is this entire thing right here, except I'm replacing with what it's equal to. Right, PQ right here, I'm replacing with what's right over here. All right, but we're going to make the same argument for now the other part. And this is also, again, substitution property of equality. Or sorry, just substitution property, not of equality. This is QU is equal to QS. Okay, that's really relating to this statement in number 3. Right, TQ, yep, I see that. But QU is being replaced by QS. Right, so TQ right here plus QS right here is equal to TU. This is saying blue plus red is equal to in the entire one of these line segments. All right, now we get to some parts here. We're saying that PS is equal to TU. So what is telling us that that is able to be true? Okay, that is the transitive property. Okay, so where are we getting that from? It's because in lines 5 and 6, we're saying, or sorry, 4 and 5, TQ plus QS, and this is also TQ plus QS. That tells us that these two things are equal to each other. PS is equal to TU. So PS right here is equal to TU right here. And then from line 6 to line 7, that's definition of congruence.
Pardon the interruption.
Okay.
If there is a Zariah R on campus,
so what we did here is we've proven the statement
your mother is here to
is line segment PS is congruent to line segment TU, that entire thing right over here. Okay, let's turn to the next page. We're going to go to number 5. So again, look at you're welcome to pause the video, try it yourself, figure out what goes where. But we have these kind of narrowed down. We have these 6 properties here. Okay, but let's go and treat this. So for this one, we have XY right here plus, or is congruent to UV on this other line segment. That's just given to us. It's just telling us that those are exactly the same thing. Let's put a tick mark there. And I'll highlight it as well. I'll say this equal to this. If you don't have a highlighter, just put a tick mark, that's fine. And then we also have that YZ, this part right here, is congruent to TU right here. Let's put a double tick mark and I'll highlight that in red. All right, so that's what it's telling us right now. We know this to be true. But what are we trying to get at? We're trying to get at that line segment XZ, this entire thing is equal to or congruent to TV. And again, I know that you can look at it, you can determine that it's true, but that's where we have to use these properties to where it is part of deductive reasoning. There is no assumptions that we're saying. We're using all these principles and properties that we know to be 100% true. Okay. So first of all, we have given. But where do we go from there? From step 1 to step 2, Looks like we don't have any line segments, no congruence. We have equal to, same exact elements. This is the definition of congruence. Right, definition of congruence says if they're the same shape, that means, right, this means when they're congruent means same shape and size. This is just saying they're the same size. Yep, they're the same size. It's just now I'm not dealing with shapes now. I'm now dealing with, right, these kind of variables, or really these represent sizes. Okay. The next part, what we have here, right, xy plus zy, this right here and this right here, we're saying is equal to the entire thing, right? Blue plus red is equal to this whole thing. And this is saying the same thing. Tu plus uv is equal to the entire thing. That's segment addition postulate. Okay. All right, I know we plugged in something. Something looks different from, right? We're looking at what is different here, right? It looks like in this thing right here, I see that UV is different, right? Instead of X, Y, we have UV. So instead of this blue part, we have this blue part. Okay, so that is a substitution. It's a substitution prop, and we replaced XY with UV, but we also replaced the other thing here. I guess I should put semicolon. That is TU and YZ. Okay, right, just replacing what's right over here. Now when we have this, we can make some assumptions, well, not assumptions here. If you look at this on the left side of this equal sign, UV plus YZ. This also says, or sorry, yeah, UV plus YZ. This says YZ plus UV. They're the same exact thing. So what can I say from there? I can say that this is equal to this. XZ is equal to TV. XZ, this whole thing, is equal to TV, this whole thing. And that is a transitive property. And if you look at your option items for number 5, there's only one more thing that we can do here. Now we're going to relate this to the actual shape itself. This is the definition of congruence. Right? If they're the same size, they're congruent, meaning they're the same shape and size. Okay, so a lot of it is I want you to look at, I know we have a lot of variables here, but it's looking at what's in common here. Right, and replacing. So we substitute it there. We substitute it here. You don't have to highlight these parts, sorry. And then we see that, right, this is congruent with this right here. And then once we have that, right, we can then prove our statement right over here. Okay, so this, very abstract, right? Normally in math, right, from kindergarten probably to like algebra 1, it's all very literal. There's numbers, there's numerical values. This, right, abstract in the sense of, right, we're trying to make arguments here based on what these shapes represent. Okay, all right, we're gonna skip the next page, but we're gonna go to I believe 3 more, so 7, 10, and 11. We're gonna do 7 where it gives us partial statements and partial reasons, but I really want to focus. The video is already quite long. Okay, you know what? We're gonna skip 7. I want to go to number 10 and 11, and I want you to just make special note of this. Is right, we don't have reasons here. You might not use all of the rows that we have, and we're not gonna do that for this one. Okay, so number 10, y is the midpoint of XZ, line segment XZ. So we can say those things are equal. The argument we're trying to make, though, is XY is half of XZ. Okay, so what argument can we make? Let's start with our first thing, which is y is the midpoint. Of XZ, line segment XZ, and that is given. All right, since you have a midpoint, guaranteed if you look at the properties, we're probably going to use definition of a midpoint. All right, so what does the definition of a midpoint say? That says that XY is equal to YZ. And that's what we put here, right? We put that this is equal to this. All right, but let's do some things with this. Now, you may notice looking at our statement here, um, I have xy is equal to half of xz. What we're gonna do here is we're gonna multiply. When I say multiply, I meant add as multiply as repeated addition. I'm gonna add an xy to the left side because I know that 2 of these things are equal to the entire thing. Let me also add an xy to the right side as well. So we have xy plus yz. This is just the addition property of equality. Okay. All right. Now, something else that we know is that xy plus yz, if you take this xy plus yz, I'm going to highlight this in red. That's equal to the entire thing. It's equal to xz. Okay. How do we know that? Because that's the segment addition postulate. Right? So we're just trying to think of like what do we have that can possibly help us here. Now, if we look at this, what can we say? I see some connections here. Xy plus yz, xy plus yz. There's the same thing right here. This is the transitive property, and I'm going to create a new conditional statement, or not conditional statement, but equation. 2xy. So I'm saying if this and these two things are the same thing, that means that 2xy is equal to xz. So 2xy is equal to xz. Okay, looking at line 3 and 4. Okay, so what does that mean? It's saying 2 of these things right here is equal to this entire thing right here. All right, that's very close to the argument that we're trying to make, but it's not exactly true. What we have here, I know we have a xy, we have a half xz. What can I do to get that? And it's just one more step here. It is the division property of equality. The division property of equality, specifically what I'm doing here is I am dividing by 2 or just multiplying by half. We could say divide by 2. If you divide this by 2, this is xy. If you divide this by 2, it's half xz. Okay. We've now proven our statement here using definition of a midpoint, addition property of equality, segment addition postulate, transitive property, and then the division property of equality. Okay, so a lot of stuff there. Okay, I'm going to treat number 11 as a UDO. Okay, but to let you know, we're not going to use every row, almost every row. Okay, that is, there's 7 steps. You're not going to have this last step here, but very similar to what we did on the front side, or sorry, not front side, the page in front of it, right? So we have AC is congruent to AC is congruent to DF, okay? And then we also have BC is congruent to DE. What we're trying to prove, why are these two things, AB and EF, why are they congruent? I'm just putting a question mark, but those are congruent as well. So we have a similar argument here. What I'd like for you to do, when you're done with that, compare with each other. You're welcome to compare your assignment on the next page. So Unit 2, Homework 8. You're going to complete numbers 1, 2, and 3, all that. I'll give you just one problem on number 4 and 5 where you have completed statements but not completed reasons. And then on the back side, there's 3 problems. I want you to complete 2 of them. You're welcome to do the ones that are partially complete. Like these are partially complete where you have some statements, some reasons, but fill in those blanks there. Same thing here. Or you're welcome to challenge yourself and complete it all for this. Okay. Now, perfectly fine, right? If you make mistakes, it's okay if you need to erase it. It's okay if you need to do this on a separate sheet of paper, right? We need to get out of the mindset of perfectionist or completionist. where, right, I think, and especially for geometry class, I think we're used to getting a lot of answers correct. This isn't about that, right? This is about, right, thinking in a different way, expanding our mind to think differently in a more logical way. So that's what this has all been building up to, okay? Anyways, I know you guys can do it. Going to get started. And email me if you have any questions. All right, bye.